Our next speaker is Sharon Rosenberg from Cadence, based in Israel. Sharon Rosenberg is a senior architect at Cadence. Received his BA in computer science from Bar-Ilan University and joined Diversity Design in 1996 to lead the hardware test bench automation revolution. Sharon introduced many of the most used UVM concepts, including agents, factory, configuration mechanism, and sequences, as the technical manager of the Cadence UVM team. Sharon represented Cadence in the Accelera UVM working group and co-authored the book, A Practical Guide to Adopting the Universal Verification Methodology, and is currently driving software-driven methodology for SOC verification and represents Cadence in the Accelera Portable Stimulus Working Group. And the title for Sharon's talk is A Model-Based Approach to Software-Driven Verification. So over to you, please, Sharon.
Okay, thanks, Mike, for the introduction. I'm just going to move forward quickly. Let me just see. Why can't I? Here we go. I'm going to cover very, very quickly software-driven verification challenges because Stefan did great work in doing so. We're going to talk about possible solution and then we're going to talk about model-based approach. I'm going to use Perspect, which is Cadence technology, to demo this approach, and then the dramatic summary at the end. So, as I said, very quickly, SOC verification, big challenge. There are some specific challenges that are unique to SOC verification, which are not there. So SOCs are not just big IPs. They have some specific challenges which are very unique to those, and I'm going to touch that. I think for some extent I'm going to complement the examples that Stefan did. So some of the challenges could be multi-core I/O and cache coherency. That's something that you need to do. Can you do that randomly, automatically, high-quality test for getting all your cache corner cases? Resource distribution that you may have, the CPU cores, DMA channels, all of these are resources, and if you want to create automatic tests, you need to take those into account and to know what tests are legal and what tests are interesting. Can I make all the DMA channels be active at the same time, doing something, but something legal? These are the kind of challenges which are unique. Scheduling and concurrency of behavior, very key part in SOC verification. Low power use cases. Let's see if I can. Yeah. Performance. All of these are key for SOC verification. These are the main challenges. Yeah, I think Stefan kind of covered this, so I'm going to move forward. This is a slide that shows the diverse users that we have. All of them need to do some work related to SOC verification, but they have their own aspects, right? Not everything is reusable, so they have their own focus, and nevertheless, we want them to be able to reuse some of the logic and communicate some of the logic to their colleagues. You have different platforms that accept different input format, different capability, different amount of cycles, and here we go with the vertical reuse of IP subsystem all the way up to on top of the operating system. So these are all the bridges that we're trying to break and enable, right? So the first question that comes to mind, if you like an SOC verification, guys, what's wrong with C? I mean, we can create Angry Birds and make millions of that very quickly. Why not just use C? Well, the issue is like that. If you want to use things on top of the operating system, then you don't have a lot of visibility of what you're doing. It's a cloud of logic. You don't see what's going on inside. You don't have enough cycles and control over things. So we need to create bare metal tests. And bare metal tests, without the help of the software stack, that requires a lot of work, a lot of thinking, a lot of coordinations of the things we mentioned before. The state machine, resource availability, parallelism, etc. So test creation is tedious. It could be a day to create a test. I'm just throwing numbers could be more, could be less, but just to create a single scenario. But now I want the same scenario with all configuration modes, in all legal power modes, maybe visiting all the memory banks that I have in my system. How do I do that if every single test is a lot of work? So here are other solutions that were proposed. Some users built some infrastructure library for bare metal. So I'm not just I'm writing from scratch every test. I have some infrastructure that could help me running on runtime. So the implementation here could be challenging, especially if you're talking about portability and reuse, because different targets have different power, different speed. Some would have a constraint solver, some will not. So your ability to leverage that infrastructure could be different. Some scenario, even if you have randomization, you need to really react in zero time. So maybe relying on offline computation, because if your core is trying to shoot traffic at the same region, memory region for cache verification, if you take decision, what core is available right now, can it access this memory or not? If you're going to ask all these questions, that test is not going to be a good one and not going to achieve its goals. So implementation is a challenge. Use UVM. I'm not going to entertain that too much because Stefan already did. How about a graph-based approach? Well, actually, I'm kind of confused. I'm not sure what graph-based means, really. There could be multiple graphs out there that are being used in so many different ways. I mean, sequences could be, UVM sequences are kind of a graph, and C functions are kind of a graph. So just a tip, whenever you have a graph-based, you need to kind of maybe question the speaker of what kind of graph you're talking about, right? Anyway, let's continue, and I'm going to show you the model-based approach. So what is a model-based approach? It's actually built of two steps. Here we have all our users and all our platforms. The first step is what we're going to create a single spec-driven representation model. So here we have a model that's capturing the rules of what's legal and what's illegal in our system. Okay, so that's the first step we're going to do. Later on, we can generate code, we can work online with the simulator, etc. The other step is to write use cases very easily, leveraging that model that we just created. So we can leverage it for test creation, for coverage, for checking. All of these could be leveraged, and we're going to show you an example of how to achieve that. So here it is. I'm going to describe right now sort of a simplified mobile model. We have a cluster of 4 CPU cores. We have memory in here, and you can see that there's various subsystems. I can get the information from a camera, an image or a video to the memory. I can send and receive via the modem, decode things to a display, receive the buffer from the USB VIP into the memory. We have internal SRAM in here, which is part of the same address space, etc. So just a simplified mobile model. And there was a question about what kind of system was verified for Stefan. So this is just representing the kind of systems we do. We do the biggest system you can think of, both in mobile industry and others. And we're talking about, 10 cores, 2 clusters, whatever it is. So, but this is just simplified one. Let me go into the details. So what we're doing is, again, from the spec, we're going to look at the camera, forget anything we know and learned so far, and just going to read the spec. And the spec is going to say something like that. The camera can do capture activity, and it's going to write the video to memory. That's what it does. And what you see here is sort of a UML, a small action in UML activity diagrams. These are not the class diagrams. These are the activity diagrams. And here is the representation of it. So an action capture writes output to a memory buffer. And here are the constraints. the kind of buffer I can write is image or video, and the kind of resolution I can write is low to medium. That's going to be right there on the spec of your camera. So we're done with the camera modeling is done, but now how will I activate it? How will I enable it? If I'm using a C test bench, well, I'm going to call a capture video firmware or driver routine with a certain parameters, right? So I have a way to say, here is how in C I'm writing, I'm capturing a video. So this is actually going to program the camera by one of the CPUs to do a video. We'll see how it's all connected. If I'm using system Verilog, here's what I'm doing. I'm calling a sequence right now. Okay, so I'm leveraging either the software driver, whether they're created in C or in system Verilog register level abstraction, and I'm going to implement that abstract action of capture. So I'm done with that, and let's talk about another subsystem. Here's the DMA. The DMA, if you read the spec, can do transfer. Well, what is transfer? I'm reading from memory. I'm writing to memory. By the way, I'm consuming, in this case, one channel. So I have a pool of 2 channels, and whenever I do a transfer, I consume, I'm locking one of the channels in here. And by the way, the data kind of the input is exactly the same as output, and the resolution is the same. Okay, so I'm just describing, because this is just a copy, right? We're just transferring, we're not touching the content. So that's pretty much it. Notice the encapsulation here. I didn't say what kind of memory it is, what's the size. Everything is well encapsulated, just capturing the description, the spec of a transfer action. Okay, so in a similar fashion, I will do all the subsystems in that modem. Well, the receive is writing to a memory buffer, and the transmit will read from a memory buffer and do transmit. Convert format is just going to read from a memory buffer and do the conversion and write it back. A decode to display will read the memory buffer and stream things to a display. What display? I don't care at this point. I'm just working in a distributed manner on the graphic subsystem. Later on, the integrator will tell me, oh, actually I have 2 of them, and let the tool randomize between them, or I'll tell it explicitly what to do. So very well encapsulated code, capturing, and I'm just going to fast forward the entire system. And what you see on the left is we kind of build basically a model. These small chunks of code eventually creates a model, and while it seems maybe simplistic and insignificant, this model captures all the legal scenarios in our system right now. A tool can analyze those and tell you which scenario is legal and which one is not. Maybe come up with some solution you didn't think of from that random space. Okay, and that's what we're going to, that's the second step of Modelbased, in which I'm using the model to create scenarios. So let's do a few of these. Let's create scenarios. Still on an abstract level, just to, again, to organize things in our heads. My verification plan, now this is not a spec of the subsystem, right? My verification plan will say, decode the video from the DDR and show on the display. This is, by the way, how verification plans are typically written. They're partial. I didn't say how the video got to the DDR, the size of the video, the format of the... This, we'll leave it to the test writer, right? That's something, come up with it. What the tool can help you to do is basically just capture this. I want to decode from the DDR, and I want to show on the display. So it's just milestones. That's what I want to do. What a tool will do, and again, Perspec is a PSS tool. So I'm showing you right now the semantic of PSS, really, right? Perspec is our implementation. Perspec will check. It has the rules. It will check that these are consistent, that you ask for something consistent. And if you did, it can create, it can show you all the possible solutions. It can create a single solution. It can create all the solutions, right? don't want things to explode. It should tell it exactly what spaces you want to cover, and it will create all of them, and will tell you the ones that are illegal, here they are, and this is why, and these are the rules that are not adhering to, and that's why they are illegal. So automatically and exhaustively create this. Now you can save, create C code, SV code, talk directly to the simulator, whatever it is, and the only point we're trying to make here is you can generate a target code, but you can also, it's very good habit to save the goals. Why? Because I may need to change the model, and I will still want to meet the same goals, right? Or the specification might change. Or now there is a new system. Let's say I want to cover all the memory banks, and now there's a new memory banks. Or I want to cover all the possible producer, and now there's a new producer. The tool will take that into account and create new thing up to date with your latest implementation. This has reuse capabilities of it. Reuse capabilities also aspects to it. Coverage. We create coverage right now. It's functional coverage, but it's functional coverage for system level use cases. So I'm not covering the packets that I got or the instructions that I got, right? I can do coverage on path. I can tell you how many DMAs were active at the same time and which were active at the same time and which were not. You probably, if you worry about exhaustiveness, you want to cover that. So these are the kind of things you can do. I can go into much more details. I can tell the tool, hey, please cover that coverage bin for me, and because it knows the rule and what's legal or not, it will. So this is sort of the next level of maximization, right? Here are scenarios, right? Let's look at the scenario concrete code. So actually in the video scenario that I may wrote, doing a capture, then a transfer, then the code to display, and then show. That's what it does, right? Someone created it. Maybe the guy that owns the video owns that. An audio scenario, I will repeatedly do receive and play. I can do repeat, I can do if, right? Here's a scenario. Here's the power. I want to do them in parallel. What does it mean? I want to randomly distribute the cores because each different core may activate these scenarios. I want to find a legal configuration. Each one of them has some dependency on configuration, and I want to do them at the same time. So that single configuration should be valid for both, right? Find a configuration that is valid for both. Don't overuse the DMA channels. Cross the power modes, which I'm going to show in a minute. All of these, and this is what you have in a system level, the constraints are all over. They're in low power, in accessibility, in the memory banks, in availability of resource. All of these are being taken into account to create that single consistent solution. This is just showing how I can say things in a UML graph. We call it composer or GUI. You can say, I want to transmit, I want to decode, I want them at the same time, exactly like your verification plan, and it will complete everything you see in light blue. It's things that were added automatically, randomly, to enable a complete legal solution for you. So there's a bunch of things that are being randomized here. The memory attributes, the video itself. Did I took a synthetic video, or I used some generator or recorded video, but I'm going to make it consistent with the rest of the scenario. The selection is not going to be arbitrary and possibly contradict the rest of it because it's distribution of the processors, etc. So multiple things are being automated in here. Here I'm just saying, you know, I've shown you this before, how I can specify how do I activate this action in a target platform. I'm just showing here that it's up to the tool eventually to create, in this graph, what do we see? We see capture that produce a memory buffer and convert format that was happening. And then this is the parallel bar of UML of showing the code to display, show, and transmit happening at the same time. You want to implement that in C, then your code, the tool, should be able to implement the same graph that I see, and I can analyze, and it's intuitive to me, into C code or SV code or whatever it is. So skimming through that, Let me talk about low power, just to show you. It's not like we're just doing selection of data paths, right? You have low power and you have state machine. I'll have to run a little bit quickly here, but here there's a power mode and a state machine, and the transitions are being described. And you want to visit all the power state, and you want to connect that with the real activity. I don't want to do a DMA transfer. The DMA is off, right? I shouldn't be doing that. So I want to create all these relationships between traffic and the power modes that I'm going to visit. So I have rules. Let's connect it to our YAM. USB transfer can take place in mode B or C. The display can be used in mode A. The modem can be used in modes D to F. I create very simplistic. Sometimes it wouldn't be explicitly written, and you'll have to use constraint to describe what's legal and what's not legal. For example, the internet could go down only up to the level of each of the other IPs or something like that, right? It's not like a discrete graph that you have. How would you model a state machine? Same actions, inputs, and outputs, same pattern. An action, a transition is an action, and I read a state variable and I write a state variable. And each transition, a little bit funny, right? But A to init just assumes that the previous is A, the next is init. A to B assumes that the previous is A and the next is B. That's how I'll define all my transitions. And I have one more thing to introduce, which is a go-to state action. This one just reads the state variable. That's what it does, nothing else. Okay. Now this one will eventually call either croutine or svroutine to initiate and execute the transition. This is a little bit abstract. It's a control knob for the scenario creator. Let's see what we can do with that. By the way, we can read UPF formats and these kind of things. So this approach of model-based opens a lot of opportunities for users in various locations. But now let's look at the second part of leveraging this model. I can say, hey, I want you to visit all the possible state machines. Please do that in one request. I'm filling the values of all the state machines. You're gonna get all the state machines covered. I can say I want to go to C, and from C go to all the possible state machines. That's what you need to do. You will visit C, and then from C to all the possible state machines. And I just want to finish with how do I connect it? Remember, we said we need to connect it to the real traffic right now. USB transfer, I must be in value B or C. Simple. Extend your USB transfer. Reading, that's the input. Reading the power state and now put in a constraint. I need to be inside B or C. That's what I need to be done. And now, if you'll drag USB read and decode to display at the same time, you will get automatic transitions on the power to ensure that the power is on. This is random, right? If I'll choose, select another state, I will get maybe a different set of sequences. All of them are legal to enable what I want, taking the power rules into account. And I can do crosses, right, of all the transitions in it with the transfer. Can I do that? It will tell me if I can. That's kind of pretty much it. Kind of show the approach of doing the modeling, the scenario creation. You can look at coverage, run on multiple platforms. There's also debug that comes with it, but that's more a tool kind of thing. Stefan mentioned the cadence and mentor contribution, which was basically the what I was presenting, and Stefan also. These are the possible values that we've seen, and these are, we were cautious in here. A lot of value for real SOC environments, as well as UVM and block environments, but real SOC environment. Productivity, the abstraction, your ability to communicate these UML diagrams, the content that you can generate. A lot of libraries could be created, portability, and measurement for coverage and where you are with the process. But that's the end of my session. Any questions at this point? Hi,
thank you very much, Sharon. I'll just see if, I think we've got time for one question because we've overrun a bit on the talk. Any questions from Bristol? There's just one question online. There's a question from John Ainsley of Doulos. PSS and portable stimulus look similar. What can you do with PSS that you can't do with portable stimulus?
PSS is a portable stimuli. I actually did the work of changing the input format to be as was voted, using both the semantic and the syntax of Accelera. So PSS is portable. What you've seen right now is a kind of a quick look at what we're working on.
Okay. Okay, unfortunately we're out of time, so there's no time for more questions. So we'll just say thank you very much, Sharon. Thank you very much.